Cool.
Yes, everything's good. So, all right. So happy to have Chia-Hsien now, who's going to tell us a little more about the Amplitude story. Go ahead, Chia-Hsien.
Yeah, so first of all, I'd like to join our speakers and thank the organizers for this wonderful workshop, as well as the opportunity to speak. So there have been already a lot of excellent talks on this subject, including those by my collaborators. So I saw that in this talk, I'll briefly highlight some key physics points that we use in the recent calculation, and I'll leave enough time for discussion. So please feel free to interrupt me anytime if you have questions. So the overall goal of this entire program is to apply field theory techniques for gravitational wave physics. And as particle theorists, we're used to think about black hole scattering. And as of now, there's already a number of different techniques, starting from the pioneering work from EOB and effective field theory to like the recent P2P map that import this scattering data into the bound state system that's relevant for like a vehicle. So of course, if we only think about scattering, it makes some perfect sense to talk about the so-called soft region, and I will give you the full answer. But with the idea in mind that I want to apply to bound state, I think it's still more useful to split into potential and radiation. So I think I share all the sentiment that Gregor just talked about, that it's annoying, but unfortunately in practice, I don't know a way that don't do this splitting for the bound state calculation. And in traditional GR, we also have the similar splitting. We also have the near and far zone regions. And the reason is that for equations of motion for the bound state, they really correspond to different physics. For example, potential will give you instantaneous potential, while when you add radiation, you will get the so-called tail effect correspond to the non-local in time potential, and also the radiation reaction force, which is truly dissipative. So the state of run in the conservative sector, we have the 4 p.m. potential with my collaborators. We also have the 6 p.m. From Tutti Frutti method and the 6 p.m. potential contribution by Worldline et al. And of course, the 4 p.m. potential results we have here, they're not complete. They're only a subset of the full physical answer. But the missing part, they were defined in our scheme. And it could be that the traditional methods are more useful when computing this tail and radiation reaction. But at least when we join the forces, we can push the precision frontier for gravitational wave physics. So in this audience, I don't have to convince you that scattering problems can give us insight about bound state problem. However, what's not clear is that why exactly are scattering amplitudes useful? Because you can totally solve the scattering in terms of classical equations of motion. And in fact, that's the approach that adopted by many of the groups here. So in this talk, I will argue that in the conservative sector, there's a very nice matching between amplitudes and the classical action, the radial action. So we can directly land on this radial action. And it manifests nice properties. For example, the mass scaling first discovered by Damour is manifest. And this single classical action, you can think about that as the partition function in thermodynamics that encode all the observables. You don't have to solve the classical equation of motion for each of them, but there's like all of them encoded in this single action. So this is of course known in the case without spin that we can get the angle and time delay. But what's more surprising is that even for the case of generic spin, we can get all these observables by the single scalar function. At least that's what we found at order G squared. And also this organization also help us in practice when we do integration, which you will see later. So I think overall, I would say that at least in the potential region, our method are scalable. So for next order, that also seems within reach. Okay, so what are scattering amplitudes? So of course, there's simply the transition matrix element between initial and final state. And when we take the classical limit, they are simply given by the classical path. So this classical action, we have the angular part and also the radial part. And the radial part is so-called the radial action, which is a function of total energy and the angular momentum. So we can compare this with the partial wave decomposition of scattering amplitude. And I will explain more where this is coming from. But you can write the amplitude in terms of this partial wave phase shift, and also in terms of decompose them into the Legendre polynomial. And in the classical limit where the angular momentum is large, on this Legendre polynomial reduced to this e to the ij theta. And we also have these phase shifts here as a function of angular momentum and total energy. So by comparing these two, you can see that the so-called phase shifts can be identified with the radial action, as you should, because both of them, they share the same quantum number as total energy and angular momentum. So when you take these phase shifts with a large angular momentum while facing gm squared over j, this is the radial action. So where does this partial wave decomposition coming from? It's coming from the unitarity. So in the conservative sector, in general, the amplitudes, of course, are unitary, and which leads to the usual optical theorem, where you relate the measuring part to the cross section, and you have to sum over all the possible states. But in the conservative sector, we can only focus on this two particle states, ignoring all this radiation part. So this phase space can be easily understood in the center mass frame, where the incoming and the outgoing momenta are the same, simply because of energy conservation. So this phase space integral is integral over this sphere. And that's why in the partial wave basis, we can simplify this integral because of rotational invariance. And in order to satisfy this optical theorem with only two particle state, that will give rise to this partial wave decomposition formula. Of course, that's something we're not using in textbook. If I only interested in the small angle scattering, so instead of integrating over the entire sphere, I can just consider approximate this phase space by this transverse part. So instead of a the two-dimensional sphere, I can just consider this transverse part of the momentum transfer. So that's a plane wave approximation. And this is actually what leads to the usual Icano approximation. So of course, we have a lot of discussion in this workshop. And if I take the previous optical theorem and simplify the phase space integral by this two-dimensional momentum transfer, and this is the optical theorem. And in order to solve this relation, you notice that these are the convolution of two amplitude. So once you go to the position space, that becomes like normal product. So this this relation is solved by this usual Icano formula. And the nice thing is, like, once you have this Icano formula, it really dictates all the iteration structure. So you can go back to momentum space. For example, I write this Icano phase in terms of the momentum space, and I have some two-dimensional integral, where I can integrate in like the longitudinal component, which later on can be localized into delta function. So that dictates the iteration structure. But the nice thing about this way of viewing Icano is that we know what are the corrections. So first of all, we know that in practice, in GR, things are not perfectly conservative. We have onshore radiation. And of course, that's already taken care of in this Icano works. You need to subtract out this the 3-particle, the 5-point amplitude square. And once you do that, then you'll get the this Icano piece. But at the same time, there's a second correction, because we approximate the phase space by this transverse integral. But that's of course not the full phase space integral. So there's a part coming from this spherical abbreviation. Let's say analog I learned from Simon Watt. So we need to take the full partial wave into account. So the question is really, how do we do this efficiently from scattering amplitude? So the idea is to analyze this problem using effective field theory. And nice thing of EFT, of course, is that it's universal and it's simple. And in particular, by consider the conservative EFT, we don't have all this elastic part. So we can just literally focus on this spherical effect. And this is the structure of the EFT amplitude coming from Chia-Hsien and Sloan. And in their organization, the finite part is the so-called impetus that played a crucial role in Gregor's talk earlier. And the propagator for this intermediate matter particle are chosen as k squared minus p squared. And the reason is very natural, simply because when k squared equal to p squared, this particle becomes on shell. So when the denominator goes to 0, this thing really cut into amplitude in the sense of generalized unitarity, and therefore the iteration structure, all the vertices are simply given by the impetus. So once I know the impetus, I can write down this amplitude to order it in a trivial way. So this basis really manifests generalized unitarity. But on the other hand, it's not so easy to see this in the traditional unitarity in terms of optical theorem, because really the phase-space integral is some integral over this delta function. So it's very similar to this one, but they're simply not the same. Delta function, delta of x is not 1 over x plus I epsilon. So what should we do? So the idea is if we consider the icono thing we have earlier, so we want to tune this propagator into something that looks like icono. And we will use a nice basis choice in this paper by Julio, Michel, and Mao. So we will turn this into this one, and then where L is the momentum transfer, and we span in the case where momentum transfer is small. So there will be some additional order L squared piece. And we simply have this series. So what's new is that instead of just keeping the leading term, as in the case of Kano, we keep all these sub-leading terms. And we'll see that that gives the correction factors to this spherical effect. So once you do that, the surprising part is that the correction comes in two parts. So you could modify the finite part, or it can give you some additional prefactor, q squared prefactor, to this iteration integral. And the surprising thing that we found is that it rearranged the finite part such that it becomes the radial action. And this additional factor comes from the spherical abbreviation. You can either calculate this from the partial wave decomposition by brute force, or you can do it in the low bar way, simply turn this delta function into the thinest one, and this will give you these correction factors. So we verified that using EFT that the finite part becomes the radial action all the way to 4 loops, g to the 5th, simply because EFT amplitudes are easy to compute. So it's this basis where we use this linearized propagator is kind of peculiar, because it's not something that manifests generalized unitarity. In fact, that when this propagator goes to 0 or divergent, the particles are actually not on shell, because it's not a full on-shell condition. But on the other hand, it makes easier for us to extract the phase shifts, and therefore it kind of makes the traditional unitarity more manifest. So, and of course, the motivation comes from the icono approximation. So that's the basis we use for our recent 4PM calculation. So just to give you a concrete example, this is the simple amplitude for anchor A at 1 loop with only potential region. And this is the thing I copied from Julio Bao and Michal. So the first line is the tree-level square scale as 1/q squared. The second line is the usual classical part for the triangle. And the third line is something that you might want to call quantum based on q squared power counting. But if you inspect this default result like close enough, you'll see that this something that you might call quantum share a lot of the same feature. In fact, all the gamma function of this delta function just literally the same as the tree-level square. So we can recombine this first and the second line into this single iteration integral. And this prefactor is something suppressed by epsilon and q squared, and something that totally match the spherical abbreviation factor you get from partial wave or EFT. So the implication is that even though this is something looks quantum, but once you map properly to the EFT, there's no quantum potential in this 1D amplitude, as it should, because the quantum part is coming from this bubble integral. But in potential region is set to 0. So there's nothing quantum here. And the structure goes similarly even to two loops where we have the similar prefactor with some different numerical value that multiply with this double iteration, the double box. And it's more relevant at two loop because now this thing can interfere with this integral. So in the way we organize things, the finite part we have here is the radial action in momentum space, and the angle is simply given by derivative with respect to b. But if you shuffle this additional piece combined with this integral, that can rearrange this finite part. And that's what happened in the Icono case, where instead, when you take derivative to b, instead of theta, you get sine theta. And you also have to rearrange the definition of b as the Asper's node. Okay, so that's the basis we use. And what are the nice feature of this basis? First, it's nice because by linearize this propagator, we factor out the two different scale. The p that related to velocity is separated from the q. So in the expression we have, we can push all the mass and velocity dependence to the prefactor, and all these integral, they only depend on q and epsilon as in dimensional regularization. So it's nice because it match well with differential equation that when we take derivative, they only hit on the prefactor. So all the integrals you can give that they are just spectators, and you don't even have to evaluate them explicitly, except for the one that actually appear in the classical physics. So and by this way of organization, it's really a hybrid matching between the two methods, the original non-relativistic methods by Chia-Hsien and Long, where you don't have to evaluate this divergent integral, and the modular integration method, where you can compute the forcing, but you have to do all this divergent integral. But using this method, we can take the advantage of both methods. And there's also a very similar pursuit by this recent paper, and as we learned yesterday. And another nice thing is that it completely manifests the mass scaling from the original insight of Damour, where the fundamental vertices have this very naive mass scaling. Each one of them scale as mass square with this Q over n correction. Even in the case of spin, we have this prefactor, and this in part of this spin has to be covariant. And you can simply do this counting for the case of one loop or the G square, and these are the mass prefactor. And when you compare with the mass scaling in original paper by Damour, the additional prefactors, and in this amplitude formulation, you can see that they're simply coming from when you convert the amplitude into radial action, and when you convert into angle, you'll get additional prefactors. So once you model these prefactors, the rest of the thing, the amplitude have a very nice mass scaling. And this Icono phase also motivate us to write down the Icono formula even for generic spin. So instead of solving observables for solving differential equation for different observables, we have this universal formula coming from a single scalar function for either the transverse impulse or the change in spin. Okay, so I'll fast move forward to the recent G2 result we have. And my collaborators already explained very nicely about all the nice features. So in this talk, the thing I explain is what exactly goes into this iteration structure. And the only thing I want to say is that the rest of the thing, they completely agree with all the known results. And maybe to entertain the audience here, something new I can show is that we also have the same result for n equal to 8, roughly the same time that we got in GR. Is simply that there's not enough space in PRL. But as you can see that some of the iteration structures are the same as in GR because ultimately they go back to the EFD. And you can see the results are surprisingly simple compared to GR. The two features here are first, there's no test particle result, and it's something known from the SUSY PPS. In particular, there are no elliptics. So in anchor A, really makes your life simpler that all these are just polylog. Okay, so with that, let me conclude. I think the main thing I want to say is that in the conservative sector, there's a very nice interplay between amplitudes and the classical action. And can either expose this connection by elastic unitarity or using effective field theory. And we have nice properties like factorization and also help us to do the integration and also motivate us for the Acano formula in the case of generic spin. So perhaps the question for the discussion is that how much of this can carry out once you turn on the dissipation? And I think this is a big open question and we can perhaps discuss more. So thank you.
Great, thank you, Chia-Hsien. Is there any question? Yeah. Please raise your hand. Maybe I can start asking you a question, and then maybe we can go into the discussion.
Yeah.
If I understood correctly, Donald, you have a question. Okay, go ahead first. Go ahead, Donald.
Okay, thanks. Yeah, so I just read these polls.
Yeah.
I mean, the 1 over p dot l. I mean, these are basically the poles you'd expect to get from the Worldline theory, right? I mean, they're just the 1 over frequency poles. I mean, you get 1 over frequency squared, obviously, but this is just
yeah. So these are decomposed into the z direction, where in the Worldline, you actually get the full p dot l, the full vector. So they're not the same. And also in this basis, crucially, I have to
but p is dominantly in the z direction, right?
Sorry?
P is dominantly in the z direction.
Yeah, but there's small correction away between this p you have here is not the same as this p.
It's shifted by some q.
Yeah, it's shifted, but q is well, yeah, maybe it's the way I think about it. Q is small, right? Q is h bar.
Oh, I see what you mean. You say if I give you the classical Worldline result, and then I do this.
Yeah. I mean, the way I think about it is there's a wave packet, so the wave packet has some slop in it of order q, but the wave packet itself has got a momentum in the z direction. So that's exactly what you compute in the Worldline theory, and the Worldline theory is the wave, gives you the behavior of the wave packet. So the momentum in the Worldline theory would be the pz. And then there's a q slop at the level of the amplitudes. That's just
so in the case of amplitude, you cannot do this because small q are still important if you have amplitude. But if I, like you say, if I give you just literally the classical Worldline answer, and when you change this, I don't think it will make any difference, except that in the Worldline, for example, from Feynman rules or equation motion, you still get all these double.
Yeah, so the Worldline spits out all of those higher order things because it's got bazillions of
you still need
vertices, right?
to clean up this double pole back to these spaces.
Yeah, I mean, the Worldline, of course, wants to give you the double pole.
Yeah.
It's one over open squared, but you know, there's cancellations because of the Feynman rules.
So yeah, it's and also I think the main difference is that when we talk about Worldlines, we have to commit to some quantities like delta p, for example.
Yeah,
and
yeah.
This is a basis acting on the amplitude. So that's a place where amplitude is really special because it doesn't commit to like delta p1, delta p2, but it's like the action.
Yeah, I don't know. Actually, yeah, sorry. I mean, maybe I'm sort of slightly converting question time into discussion time, but apologies. If the chairman will permit me to keep talking.
You're above me here.
Yeah, I'm gonna accept that. Certainly not. Yeah. So. Yeah, I mean, maybe one of our Worldline expert friends, can say more. But couldn't you set up an amplitudes for the Worldline? You just switch on quantum of the displacement. I mean, you expand X around some vacuum, straight line, or something like that.
That's what supposedly Gustav and Jan are doing, right?
Yeah, but I mean, yeah. So I mean, could you then just match amplitude to amplitude?
Oh yeah, I see what you mean. You're saying literally compute the classical action in Worldline.
That's what they say they should be.
Compute the amplitudes in the Worldline.
Yeah.
But that's what they claim they're doing, right? That they get to the chi, and chi is supposedly this guy. But
yeah, but I mean, okay, that's going through chi, but I wonder, can you just do something that's a bit more direct? I don't know, maybe just
but it's
just to simplify the comparison.
Is amplitude something well defined?
Well, yeah. Well, yeah, I don't know. I mean, I can lay down a couple of sources for these displacements.
They give a formula, right? They give a formula in their paper that you need to do LSZ, and then you get.
Yeah. That makes sense. Yeah, you just take these things on shell and then just directly compare to the amplitude.
Yeah.
So I understand how to do that for like say impulse.
I mean, you could do it. I mean, at the level of the impulse, but in a way, or whatever observable. But it would be nicer to just do it more primitively at the level of the scattering object. At least from the discussion. Oh, hi, good stuff. Yeah.
Actively give you.
Maybe I should say so. No, so the relationship, as we understand it, is the 2-to-2 amplitude as it compares to the iconal or the radial action. That's the relationship which we derived and which works at least up to 2 p.m. At 3 p.m. we can derive the iconal, but there appear to be some 1/epsilon poles which we can't account for.
I mean, is there a reason why you can't just set up something that's really like an amplitude? Yeah, it's just
what do you mean?
Well, I just mean,
I'm confused. It's like
the expressions look very similar. Yeah, if I take an amplitude like Chia-Hsien is doing, and I expand it around these poles, right? Those poles are want to be the 1/omegas you're going to get by inverting the d2 dt squared in the Worldline effective theory, right? Yeah. So
yeah,
Chia-Hsien's computing an amplitude. I like amplitudes. So why can't I just compute something that is directly the expansion of what Chia-Hsien is doing?
I think they already computed this action.
I mean, the difference is that in the amplitude, you actually have an ingoing and outgoing state representing black holes, which you.
But I suppose, I mean, you still have particles. I can create them and scatter them, right? They're stuck on a Worldline, but I can still scatter them.
That's well, I mean, yeah. So we do compute where we have an outgoing line. That's how we get the deflection. No, we think of the black hole as a background.
Yeah. You kind of have to, right? I mean, you have to expand it at some vacuum.
Exactly.
Yeah.
Okay, I'm gonna intervene.
Okay. I'll shut it.
Maybe one comment before we change topic. So something that is crucial here is that these are 3D integrals. These are not 4D integrals. So the time dynamics is trivialized. So the way I think about this is more like solving the time-independent Schrodinger equation to get the amplitude in the EFT.
Yes, that was my question, because that's how we did impetus. And that was how I was going to ask you, because we prove it to all orders by iterating. Yeah. And you said for loops, if I understood correctly. So you don't have an all order proof?
Well, the only step that you need for an all order proof is the only tricky step is this arrow that Chia-Hsien has in this slide. Like how do you control that expansion from the delta functions where you have k squared minus p squared to the linearized delta functions? This is something that it's stated always in the literature that this can be IVP reduced to a basis where you only have delta functions and not derivatives of delta functions. We are trying to understand that statement.
Yeah, so maybe to rephrase that, you can say we have a trivial order proof that the phase shifts is the radial action.
No, I know, but we even say in our paper, sort of, and then with that's okay.
No, but the sort of is the key point, right? Because to say, oh, there's an exponential at leading order, every exponential is the same. No, you need to understand the subleading orders, and we understand up to 4 loops.
Yeah,
and we believe we understand it to all orders.
At 1 loop it works perfectly fine. At 2 loops you're gonna start failing, right? Yeah. And I agree. What is nice of what you guys did is reorganize this calculation so you can see this radial action popping up. And in J space, which is the conserved quantity, which is the fact that we were doing an impulse in B space, and then this is mixed. It's completely fine. Now impetus is more natural because it's just a Schrodinger equation and you can prove it to all orders. And it'll be great to see the same here happening to all orders as well. That's what I was asking. But it has to work. I completely agree. It has to work. You have to
the proof is simpler in the sense that it's just a semi-classical approximation. So in a sense that the proof is what Chia-Hsien had in his first slide. You don't need to prove anything else. But the proof that we want is a proof that tells us how to calculate, which is different. So the formula is proven to all orders that.
No, but you have an IR finite piece. We had to prove that the IR finite piece with a very specific prescription was the impetus formula. That's what you need to prove. The semi-classical thing, yeah, get fine. We all
so that's what I'm saying. That the only tricky part is because our exponential involves these 2 particle cuts. The only tricky part is when you expand the exponential. It's always clear that the thing in the exponential will be the radial action, just from the semi-classical approximation. What's tricky is to say that that thing remains as the finite part. So the exponential is always the same. We understand that it's the 2 particle cuts that will give you, but that doesn't help you calculate. So in a sense, it's a useless proof. It's a proof of exponentiation, but it's a useless proof. The useful proof is the one that tells you that when you expand the exponential, there's no contamination into the finite part. And that's the proof that it's slightly trickier.
Yeah, or maybe to rephrase the question, the thing I want to show is this exponentiation in the partial wave basis, how you map this nicely when you go to momentum space.
Exactly. That's why it's not like impetus, which is a straightforward.
Yeah, impetus is much more straightforward.
Maybe
to Donald's original question, I think what I say here is actually irrelevant for Worldline. Simply because in Worldline, you just literally get the classical action. You don't care. There's no iteration. So all these like rearrangement for fixed order amplitude is simply not there for very classical quantities.
Yeah, no, I mean, I'm just trying to understand, and that's, I mean, I think, you know, there's a very sharp argument that you want to get some 1 over omega poles from thinking about Worldlines. You know, you can write the poles in some other way, right? I mean, it's just resumming.
Yeah, but in the end, you can evaluate them onto it like the classical answer. In the end, they're literally this classical part.
But the question by Donald is interesting because it connects to what Gustav, Jan, and company are doing, because we would like to know what are the rules for that guy to begin with in our formalism. We can do it perturbatively, but it would be nice, just as Julio was asking, just target that guy directly.
Yeah.
Right?
Yeah, I mean, I think we all agree.
I mean, conceptually, it's cleaner. I mean, in practice, it doesn't make a difference. By conceptually,
but what you do is to avoid this issue, right? Like when you calculate this amplitude, we need to worry about these iterations and how to organize finite part, higher divergent part. But because you know Feynman, you have Feynman rules for the exponent directly.
Yes, exactly.
It's something that we don't have in the amplitudes case. So you can just calculate the semi-classical action directly. That's what, I mean, you take this extra derivative that we were talking about, but you don't need to, and then you would calculate directly the semi-classical action.
No, but that's only the radial action at a given order if you understood the previous guy. Otherwise, there are iterated parts that you need to calculate anyway. And that's why this impulse is taken care of. like the chi-square, chi-cube, and so on, right? So
yeah, but I think that if you, I mean, the way you do it is you actually solve equations in motion. The way that, but in principle, one can calculate it also like Gustav does.
But you still need to replace it by E and J with some order, right? So you need to compute that guy and say, this is the correction to my previous order. I'm gonna use the conserved quantities of the previous order to plug it in there. And that for sure, the integral of that guy is the radial action. I agree with you. But there is a lot of inputting back, which I can just get through my machine of the impulse, right? Without thinking, right?
Well, I think that's the way you think about it, but the way that Gustav and friends do it, there's no plugging in lower order equations of motion. There's just a final rule for the deflection.
The iconal doesn't work. That formula is wrong. So we
don't. I would say that one has to understand if the calculation that they were doing is literally the semi-classical action or it was some other quantity.
Yeah, I think it's more related to the radial action to the iconal, but that is I haven't yet fully understood. I'm exploring that, but it's unrelated to this. But I agree with you. It'd be much nicer to have the rules for that guy directly. For me now, it seems like the impulse seems much more systematic and Gregor has it all, it's structure. But otherwise, I mean, we will have to think a little more, which is fine. At some point we do more thinking, but now we just want to crank it up, right? And this seems to be.
I can make one comment here because we do know, at least to some extent, what this comes from, and I think it's very closely related to what Raphael's saying. The point is that when you look at the impulse, you can use retarded propagators everywhere, whereas when you look at the iconal or the radial action, you don't have an outgoing line, so it no longer makes sense to use retarded propagators, and this is related to a different choice of boundary condition. I'm fairly confident is related to what's going on.
This is conservative, right?
Yes, it is just conservative.
Why does the I epsilon matter here if this is a conservative process?
It's not in that. It's not conservative versus radiation. It's to do with how you define your the impact parameter, the velocity, the variables your worldline depend on, whether you define in terms of incoming states versus intermediate states.
We can come back to that. This is
yes.
Okay, good. So is there any other question for Chia-Hsien? Otherwise, we can use whatever time we have left. So Gabriele, how much time we really have for this?
As you know, at 5, we should in principle stop. So not too much time. But as I mentioned yesterday, we can continue tomorrow when we have a lighter program. Unfortunately, I think you told me that you are unavailable tomorrow.
It's a little bit difficult tomorrow because my wife comes back from work at 6. But
we'll discuss in your absence, which will not be the same thing.
A lot more silent.
You talk a lot, Donald. Come on.
I think that's a compliment.
But anyway, go ahead, and then I mean the talk at 5 could be also of interest to us.
Yeah.
Jan and Ricardo talking.
No, I agree. Okay, so very brief.
Okay, so let's open the discussion on.
So let's thank Chia-Hsien and Gregor again for great talks, and let's open the floor for discussion. So I don't know exactly what do you want to emphasize more. So there's the issue of the boundary-to-bound dictionary that Gregor talked about. We understand it very well when we have local contributions. We understand it very well from potentials, and we understand what we call the local part of the tail, which is not the log of omega, but everything else.
May I? Yeah. Let me ask a question just from the, not from an expert point of view. So is this connection something you show formally at the general level, or you do it order by order for the conservative part? I mean, we have a nice way to see that analytic continuation brings you from one to the other, irrespectively of a PM expansion.
Well, as long as there's a one-to-one solution, I would say yes, because with the angle, I mean, you can get all these loops and so on, right? So you have to invert. So I would say that we have an all PM order proof, because this fields of formula in principle is general. We show that the orbital elements are connected. That is in principle general.
General in G, in G Newton.
G Newton, exactly.
It's exactly in G
Exactly.
Newton.
And we have examples, for example, the scattering angle in Schwarzschild, which resumes all the corrections a leading order nu. That one also works. I give you the full exact scattering angle in Schwarzschild, and I can predict the periastrum advance exactly the same way.
Yeah, no, that I believe. If you are in this probe limit, it's quite clear.
So we have an all PM ordered proof as long as these functions are well defined, let's say.
But it's always restricted to the conservative part.
No, then we have the energy. Also,
then you have the energy, but
we also have the angular momentum that we can relate. That's new, that has not been shown, but it's the same proof for the energy. Maybe Donato or Tio can correct me, but the proof, the expression that they give in their paper, I think they checked that it works in post-Newtonian. I did not see a proof to any post-Minkowskian order, but it works. And we can prove it because of the orbital elements, also to all orders in post-Minkowskian, because of the features that Gregor also emphasized, that the integrand, which is d dt, has a j minus j symmetry. And for the orbital angular momentum, it's j minus j. Mm-hmm. So when you do the orbital elements, because you are evolving on the conserved solution to compute the flux in this adiabatic expansion, therefore you just use the orbital elements of the conservative solution that we know how are related. So just the properties of the symmetries of the fluxes allow you to run this B2B map.
But I think it's important that you write the fluxes in the right variables, right? Because, for instance, if we calculate the
conserve quantities, right? G and E, yeah.
Yeah, but for instance, if we calculate the flux using KMOC, right, we would get the flux in terms of the angular momentum, E, but instead of R, we would get it in terms of the time or the frequency of the graviton.
Right? You talk about the spectrum, not the total flux.
Yeah, the spectrum, the instantaneous flux.
Yeah, no, right? You have to write in R because it's an integral in dr. That's crucial.
Right. But that might not be so simple, because then you need to basically go to the time domain and then invert like the dependence on time of R.
Because dt and dr, there's just an r dot, and the r dot is d by dpr, and all it's symmetric. The j minus j symmetry goes there because p square has it, and then pr has it.
No, I'm talking. I understand that, but I'm talking in practical terms. If I give you a flux, an instantaneous flux, which is written in terms of energy, angular momentum, and frequency, how do you use that?
I integrate. You get the total for the elliptic, and then I can give you what the integral of the hyperbolic would have been. And by
but then you need. But only the integral, or also the instantaneous in the time domain or in the frequency domain.
Exactly. The instantaneous is the same. It doesn't care about which orbit you're in, right? The difference is what you integrate on. The boundaries are the difference, right? The ddt is identical for both, right? So what matters is like the total radiated power when you integrate between minus and plus infinity, or when you integrate on 2 pi, is related by analytic continuation. That's the catch.
So I understand that the total flux is the integrated flux is related, and we use that in an appropriate fact. But what I was asking is if the instantaneous flux.
That's the same.
Yeah, but.
What do you mean the same? It's also related by analytic.
No, it's identical. dt doesn't matter which orbit you are. That's instantaneous.
No, but importantly, only when written in the right variables.
No, in the conserva G, E, and J. What is this letter? J, E, and R.
Yeah, but that's what I'm saying. That's when we computed using scattering amplitudes, the natural variables that we will compute it in is not as a function. Like you write it as some function of the multiples that have the implicit time dependence inside of R, right?
Yes.
The way we computed in amplitudes would be as a function of the frequency of the emitted radiation. So there's some extra work involved.
Yes, because the frequencies are even discrete in the elliptic case. In the other case, it's a continuous function. So it's not obviously how you go from one to the other. You have to be careful with the Fourier transform and so on. No, I agree.
Okay.
So I think maybe the way to do it, you still need to know about the fact that you're in scattering dynamics, to invert that to write in terms of R. Basically, you want to.
What is R?
R is the separation between the two bodies.
Oh, okay. Sorry.
So the formula is that the observation is always the same, that the integrand of all of these things.
Yes, but there is something, Julio, that you already have. DEDT, we already have at 3 loops. It's sitting there in the answer in front of the logarithm, right? So we already know what the flux is. We don't even have to do all what you just described. DEDT is known. We know it already. It's in front of the 1/2 epsilon. So we don't have to do anything.
Integrated, it's a total delta E.
No. If you go to the C4 coefficient on the Hamiltonian, there is a pole 1/2 epsilon. That is DEDT. And we checked it already to all PN orders. So we already know the flux, and we're going to put it in our paper because it's obvious that because the integral of the Hamiltonian dt is the radial action at this order, right? And that has the total flux 1/2 epsilon. So that guy is the flux. And we checked it. We check it's beautiful because actually I can predict what the G Newton corrections are because we know the flux to so many orders that I can correct that logarithm to any PN order that we have right now. So we know so much more from that answer. We know the instantaneous flux.
Yeah, but this is using a trick, right? This is using this relation between the tail.
Yes, so exactly. This is using the tail trick, yes.
But I'm asking if we were to, like, once we can't use the trick anymore, maybe and by the way, I want to do a 2-loop calculation, not a 3-loop calculation to extract the G cubed.
I agree. Actually, I want to do a 3-level calculation, which is the way I will do it.
No, but that is cheating because you still need to do some integrals. Come on. I mean, you can say it's just the, I mean,
3-level matching.
No, that's just not true, right? Because you need to do the angular integrals.
No, time out. The quadrupole moment is mxx, and I just have to use accelerations for Newton, okay?
No, I'm asking you in PM.
Yeah, I can 1/r potential from 1 PM and get the full answer.
So how do you write that?
The 3-level answer for the accelerations and the quadrupole. You just need the no G Newton corrections to the quadrupole. You can even do the Tij and square it, and it's even simpler. Right?
No, I'm asking you. I mean, I thought you were saying that you're writing the flux as a sum over multiples, but that is only.
Huh? Yes, I'm saying that if you knew how to do that sum, you could even just use.
Yeah, sure. I mean, of course.
Or you do Tij and you just do the cubic, which is what Massimiliano is playing, and that is 3-level matching. And you just square that. So
you just square that and do an angular integral again. Like you need to do an angular integral to get
the full integral, which is not trivial. But finding the integrand is in principle straightforward, right?
Sure. I mean, okay. That's a big difference. That's what I'm saying. That the integrand, I agree, is a 3-level calculation. It's the 5-point amplitude squared, right? We use that as a unitarity cut in our calculation. So of course that is trivial, but that is not the instantaneous flux. Like the whole discussion is about how to do those integrals, right? Like we explained how to do all the integrals.
Yes, but in that case, Julio, if I rewrite that integral, when I have the e to the ikx, instead of going to frequency space, I stay in time, right? I can then rewrite that as R and put it on a bound case and get the flux, DEDT. Because that
so I understand that analytic continuation will work. I'm just saying that the natural thing that we would compute, where you need to find a way to do the integrals, which is what so far no one has done. Like everyone has the 5-point amplitude squared, everyone has the integrand, but
that's because we decided to finish. The integral is actually quite simple. It's in our basis already. Now
but there's more scales, right?
Huh?
There's more scales.
No, because for computing what? For DEDT or for computing the total guy?
DEDT.
Okay, DEDT is different. Yes, I agree. But for
so that's what I'm talking about all the time. The integrated flux, everything is understood.
Okay.
It's instantaneous flux.
What is actually the conclusion of this discussion?
The conclusion is that it's still non-trivial to calculate the instantaneous flux. And even if we calculate it in scattering, there's non-zero work that will make that useful for the bound problem. Because what Rafael is saying is if you write it in terms of J, E, and R, it's the same, but the way we would calculate it, say using KMOC, wouldn't be written in terms of J, E, and R. It would be written in terms of J, E, and P, or the frequency. So that one still has to find a way to rewrite that in terms of R.
But it's also important to stress that we already have DEDT sitting in the answer in front of the pole.
Yeah. Okay. That's a different observation, which is a very good observation.
So actually, I want to ask about this more because I still have the same question as Damore, because the one over epsilon prefactor is the flux integrated over the scattering trajectory.
The radial action, but in
Yes.
your Hamiltonian, it's dEdt.
Oh.
We already saw it. I already checked it, and it works beautifully. But it was in my talk, by the way, if you didn't pay attention. So I said many times that the radial action was the integral of the Hamiltonian tail, and the Hamiltonian tail is the flux, dEdt. And that's why this continuation works.
What about dEdt d2 omega?
That I don't know. All I know is who dEdt is right now. I can give you the expression because
integrated over the sphere.
Now we have it without integrating anything, right? The Gabriele, that's what I just said.
No, but it's integrated over the two sphere.
It's integrated
over the direction.
No, it's dEdt. It's p squared over r to the 4 g cubed.
It's no. What Gabriele is saying is that in that quantity, the angular integrals are done.
It's the total dEdt, but Gabriele wants the angular
dEdt. I mean, what you compute with the, I mean, the waveform gives the whole thing, right? The angular distribution as well as the frequency or time.
Yes, this is the dEdt that has functions of p squared, the same way we do in Pn.
So it's a function also of direction?
No, because we're in the isotropic. It's an isotropic. So there's a p square, a function of p square, and there are g or j square corrections if you want. But there are j over r corrections. So instead of having
this is a trick that only works for dEdt, and you need to go to one higher loop.
Exactly.
The question is, how do you do this at the loop order where it shows up first?
Yes, this is a trick, which I don't know how to do. I just realized that it works and it's beautiful because I get dEdt to all orders. But how to do it, I agree with Julio. I don't know. But I get a function of p squared, Gabriele, that usually is written in Pn. It's written as p squared and pr squared, like p dot n squared. But we're going to the isotropic gauge, so that's traded by g over r corrections. So essentially, we have the 1 over r to the 4 to all orders and p for the dEdt that matches all Pn orders. If I look at dEdt in post-Newtonian, I get all the orders in 1 over r to the 4.
Sorry, at which order are you talking about that you have d already?
It's the leading, right? The g cube in the dEdt, but to all orders in p squared, p4, p6, p8, all of those.
I think so. Just to summarize, maybe there were 2 points made here by Raphael and other people. So the first one is that our Hamiltonian already had the g cubed flux in it. We just didn't point out that
yeah, but you have to be careful because if you get the factor of 2 wrong, you get the flux off by 2.
Yeah. But then the other observation is that we still don't know if we do an amplitudes calculation of dEdt or any calculation of dEdt at order g cubed for scattering, and it's not written in terms of r, or similarly for the angular distribution. So if we calculate the angular distribution at g cubed, there's still no way that we understand how to take that calculation, which would be a result written in terms of frequencies, not radial separation, and then translate that to the bound problem, right?
Yeah, that's different.
I mean, I think you just can't do that, as you just described it, right? But it's not like you can't use amplitudes to do it. You just need information from the 4-point amplitude too. I mean, it's the 4 points and the 5 points together, not one or the other. It's just the same as the way you do it classically, the flux and
what you can do, what you can do, what you can do, Julio, is do the same we did with Firsov and invert. You can then compute the total radiating energy and cook up what dEdt gives you the right answer, assuming that.
Yeah, but then you need to know what is the right answer for that.
Yeah, of course, you have to make an answer. Yes.
Yeah,
exactly.
And that's complicated, but yeah. I think, I mean, I agree with Donald that this involves 5-point amplitudes, which is how you guys wrote the formula and how we computed it for the integrated flux. There's a very similar formula exists for the instantaneous flux, but again, it would be a function of the frequency of the graviton, not of the radial separation. So I think one needs to still kind of invert the dynamics
Yeah, I mean, there's potentially more than one way to do this, but you know, a complete approach would involve information from the 5-point amplitude and the 4-point amplitude.
Yeah.
Okay, finally, so because we're gonna get cut off, right? The other thing is this order epsilon corrections, right? I mean, they are there in the logarithm, and they give you this factor of 2 off, right? And there are a lot of finite pieces as well. I agree that in this particular case, because we know the tail, we know a lot of these ambiguities are gonna get canceled. In general, through the IVPs and so on, we try to subtract them, we really don't know where they are. So we know that the integrand at order epsilon, we can just remove, but there's a lot of other corrections that we cannot just track. And that I agree is non-trivial. But what this really tells us is that the answer that we're getting now, that we agree with you guys, is completely unphysical. It should not match anything. It has a lot of spurious terms, right? So I'm very surprised that you do a matching with numerics and it works, Alessandra. That makes no sense to me. So I think it's when we try to do the full soft and we understand the answer, then we're gonna get it worse because it should be.
Rafael, most of the answer is not scheme dependent, right?
No, I disagree. There's a very large factor that is non-zero from the order epsilon pieces. Just the log, for example, is wrong. You get twice the log. So that's already wrong. And
but only single logarithms, only things which are transcendental weight 1 or constant, right, are scheme dependent.
You're thinking as an amplitude person. I'm thinking as a PM person. Those are large chunks of the answer, which are numerically not small, which are not giving you a small correction.
So what is bigger, log of sigma or log squared of sigma?
No, but they removed the log. They didn't even put the log, right?
No, I'm talking about the finite parts. I'm just saying that this
missing, and there are factors, corrections, numbers that are finite over there. That I don't know. I have to look at the polynomials what they really are, but there's the same order type of corrections. I do not see a big difference.
Well, the difference is that the scheme dependent part of the answer is the weight 1 part of the answer, because it's what you get by fiddling around with the coefficient of the 1 over epsilon.
Well, but that's what I was saying earlier. It's because the tail, we find the tail to have transcendentality very low. There is nothing really in the tail. That's what I said, what Gregor said. But that doesn't mean it's a small correction, right?
By the way, Rafael, I mean, we did explore how that curve varies, and I think you should take that slide as it is written, not as your personal interpretation, because it is written very clearly that it's just an example.
You subtracted just the pole. You said literally, you subtracted just the pole.
No, I'm saying that it was presented as an example following a certain prescription. If you are taking it as, it agrees very well with numerical relativity, and I don't understand why you are just extrapolating what that slide contains. You see the point?
No.
It's an example.
No, I don't see the point. You subtracted the 1 over epsilon and made a plot.
Let's not have this discussion here, maybe later.
Right? No, but maybe I don't understand what was done in the plot.
Yeah.
Okay, maybe that's the point.
Okay, sorry, I don't want to hijack the whole thing. We should cut off and come back on Friday.
We should cut off and postpone just by 1 day to 5 p.m. tomorrow, and